Okay, Euler and Hamilton. A Swiss and an Irishman go for a walk. Now, literally, one of the most famous things that Sir William Rowan Hamilton did was actually go for a walk. And he was walking his dog, and he suddenly had a major brain wave and didn't have a pen and paper with him, so he scribbled it onto a bridge in Dublin. And there's a plaque there. You can see on the picture we've got the plaque here. And then he wrote this beautiful equation down here. And you'll be like, what the hell does that mean? What does that mean? What does this mean? Well, it's about four-dimensional space. So it means when you're playing Tekken, that bear looks totally realistic and it looks like a three-dimensional thing that can spin around and stuff. So instead of being flat graphics, you actually look like you've got a 3D object being displayed in 2 dimensions. So thank him for Tekken 2. Now, Leonhard Euler, it is pronounced Euler, by the way. That's what it says here, Euler. And if you want to, you can listen. If you go to the Wikipedia page and click the link, it'll tell you it's Euler, not Euler. He was one of the greatest mathematicians of all time. Generally, there's a joke in maths. It's a hilarious joke that everything in maths is named after the second person to discover it, because the first person was probably Leonhard Euler. Okay, so Leonhard Euler did spend some time in a place about here, which was called Königsberg. But, you know, World War II, it became, went from being part of Prussia to being part of Russia, and then part of obviously the Soviet Empire. So Kaliningrad is what it's called now, and that's that little triangle of Russia. That's Russia. That's a bit of Russia over here, and you can see it's disconnected over here. But they wanted to make sure after World War II that the Russians could have sail their ships out to attack people. So that's why they got that little bit of triangle of land. Now, before World War II destroyed all the bridges and got it transferred to the Russians, there used to be these bridges across. You can see there's some pictures on of the bridges here. And so as a fun game, they used to try and work out, could they go around Königsberg, cross every bridge exactly once? And Leonhard Euler proved that no, you can't, because he didn't have anything to do because no one invented Tekken yet. Now, as I said, Euler was about the bridges. So Euler is every edge. So Euler's all about the every edges, because that's what he's doing in that problem we're trying to work out with the bridges. Hamilton, on the other hand, is about the vertices. So he was an Irishman apparently, and he discovered this maths when he was trying to work out how to do a tour of the Highlands of Scotland. Can't imagine why an Irishman would be touring the Highlands of Scotland. Insert your own ethnic stereotype here. Now, I'll actually leave you to read all those things, and we'll refer back to it later, but that's a nice summary of what's going on here. The important thing to know about Euler trails is you can only have 0 or 2 odd vertices. Now, in some textbooks, it's sort of implied that 0 doesn't count, but it does. I mean, because an Euler circuit is also an Euler trail, which is also a trail, which is also a walk. You know what I mean? It's the same sort of thing. But an Euler circuit has no odd vertices. And that's pretty much the only maths we can do, even for the Hamiltonian side over here. Hamilton is just a matter of just suck it and see and work it out. That's all you need to know. Now, this one is just saying which one is not a path. So can you follow the order of these letters and via the connections? So this one says, A says PRQTS. So PRQTS. We can do that. So it is a path. So we say no. Then we try the next one, which is PQRTS. We can do that. We did that. So let's get the actual eraser there, not the pen. So we can do that. So it's not the right answer. Then we've got PRTSQ. We can do that. So it's not C. Then we try the next one, which is PTQS. And we can't get to R. So it looks like D is the correct answer. But would be good study bugs. And let's try the last one. PTRQ. QS. We can do that one. The correct answer was, of course, D. All right, we have the town of Zenith, and we're saying which one of the vertices on the graph has a degree of 4. Just by eyeballing it, it looks like that one, F. There you go. That's the famous eye and brain combo attack. Now it says for an Euler trailer to exist, what is the minimum number of edges that the graph would require? Now the point is here, like, let's just do all the degrees. So that's 2, 3, 2, 3, 4, 3, 3, was that 5, 3, and 2. Okay, so how many odd ones do we have? All right, so the odd ones, we've got 1, 2, 3, 4, 5, 6. Now, listen carefully to this one. If I take these two and join them, they become 4 and 4. So that would be one edge. Then I could take these two and connect them, and that would be 6 and 4. So we're pretty good. So what is, for an Euler trailer to exist, what is the minimum number of edges to add? 2, because that leaves us with exactly 2 odd edges. We're allowed 2 odd edges for an Euler trail, so therefore we're all good. It says Hamiltonian path. All right, on to Hamilton now. Now the important thing is we don't repeat a vertex. Okay, so the postal worker has delivered the mail at F and will continue her deliveries by following a path from F. So you got to start at F. So you could just go. There you go. There's one. There's more than one you can do. When my pen's working. So F, you got to go on like that. That would have been fine. It must have been a nightmare to mark this one because there's just quite a lot of possibilities. You got to go on like that. Those would all be possible. The inspector will leave the town P to check all the roads. That means the edges, and return to town P, which means edges is Euler, returning is circuit. So they're telling you you need to do an Euler circuit. And they also tell us we want the minimum distance. So whatever our Euler circuit we're going to be doing, we need to be making sure we get the minimum number. And Euler circuit is no odd vertices. So problem is odd, 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 and odd. So to make them not odd, you'd have to add some extra edges. So that's what I mean by travel on the roads more than once. If I add here, then I'd have to add here, which is no good because I'd be adding a 14 and a 20. But if I add one here, just repeating that road 10 and repeating that road 12, you can see that now all the vertices are even, and so you need to repeat the roads ST and PQ. That's why I've repeated them, got the multiple edges. So how many roads will the inspector have to travel on more than once? 2. Now we've got to determine the minimum distance that the inspector will travel. So we said we were going to repeat this one and repeat this one. Now this is where people could easily make a mistake, and when your brain gets a bit tired and you've been making lots of videos, you probably might make that mistake. If you're visiting every edge, you don't have to work out the path that you're traveling. You just need to add up all the numbers. So 6 plus 7 plus 8 plus 9, that's the middle ones, plus 2 lots of 20, plus 2 lots of 12, plus 20, plus 14, and then you grab your calculator and work that all out. And you should get the value of 108. Don't forget your units, kilometers. So again, you didn't need to work out the path, because if you're going to every edge, then you're going to every edge. You just add them up. It didn't say tell us the path. It said tell us the total. So if you spent time working out the path, wasted your time. Now, again, this one's nice because they said Euler trail. So at the most, we can have 2 odd vertices. Now, if we look This one's got 1, 2, 3, 4. This one's got 3. This one's got 5. This one's got 4. This one's got 1, 2, 3, 4, 5. And this one's got 1, 2, 3, 4, 5, 5. So you can see we've got a situation of odd, 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 and odd. So we just need to figure out which lines can we remove. So we could have removed this one, and then they'd both be down to 4. So that's one way. And then, or we could remove this one, and then they would both be 4. We could remove this one, and then there'd be 2 and 4, and that's okay. And then we could remove this one, and they'd both be 4, and we could remove this one. So any one of those could be removed. There's no way of connecting anything else there. So that looks like we've done 1, 2, 3, 4, 5 colors. So the answer was in fact E. This question here with our old favorite, the one that is not true. We got 6 vertices, no loops or multiple edges. What can we do here? Now, if we've got just do 6 vertices, 1, 2, 3, 4, 5, 6. If the graph is a tree, it has 5 edges. That is true because vertices minus 1 does equal edges for trees. And you can prove it. Look, 1, 2, 3, 4, 5. So that is wrong because it's true. Next one, if the graph is complete, it has 15 edges. Triangular numbers, look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if you do actually draw it all out, because you've forgotten triangular numbers, you'll find that that one is in fact true. If the graph has 8 edges, it may have an isolated vertex. So 1, 2, 3, 4, 5, 6, 7, 8. That looks good, and I've got my isolated dude here, so it can be done. It doesn't mean you have to connect them all up. We could have our multiple edges. If the graph is bipartite, it'll have a minimum of 9 edges. Well, no, bipartite graph, you could just go 1, 2, 3 like that. That'd be 3. So confusingly, it looks like it could be D, but it's always, if you're not sure, because we haven't done much about bipartite graphs yet, put a little question mark. If the graph has a cycle, it'll have a minimum of 3 edges. There's a cycle, 3 edges. Remember, these guys are just isolated dudes now. So, but that is actually true. So it's wrong. So it looks like the answer was in fact D. Okay, consider the planar graph below. Which one of the following graphs can be drawn as the planar graph above? This means isomorphic. The easiest way to do this is to look at the vertices. So always circle your vertices and work out the degree. We've got 3, 3, 3, 3, and 3. So everything must be 3. So look, 3, 3, 3, 3, 3. That looks good. We've got 3, 4. Bye-bye. 2, bye-bye. 2, bye-bye. And so we got 1, 3, 3, 4, bye-bye. It must be A. That was pretty quick, wasn't it? Okay, we have a network map here. The tricky area in this question is really dealing with this part, but we'll get to that later. Let's start with the easy question. Starting at Beachton, this one, which 2 suburbs can be driven to using only one road? 1, 2, they are Aluma and Easy Side. Done. Okay, so we have our map over here, and now they're showing it as a graph over here, and they're talking about vertex E. All right, so if we look at vertex E, which is Easy Side, it says one of the edges is missing. So add the missing edge to the graph above. So if we think about this, if we're at Easy Side, we can go to Aluma 1, 2 ways, and we can see we've got 1, 2 ways there. So that's all good. Let's try going to Beachton. There's only 1, there's only 1. That looks okay. Let's keep going round. So if we want to get to Dove Nest, we can go 1, 2, 3. Now you might not have spotted that, so let's just check if there's 3 are there. So it's 1, 2. We need another one in there, and that's the one that's missing. Helps if you get the right pen. And so we need to do another one like that. And so this is just a common trick, because you kind of get used to the idea of going, oh, I can go 1, 2, and, oh no, I'm going up there. But you can go up there and back down there, and that does count on the graph on the right. So that's our missing edge. So what does the loop at D represent? We've got a loop here, and that's actually shown on the diagram here. You can go like that, you see. So basically, what you can do, you can return to Dovenist without visiting another suburb, without going through. Done. So Nathan begins at W on our network, and he's following an Eulerian trail. So basically that means we need to have only 2 odd vertices. Technically you can have 0, but almost all these questions are about that notion of 2. If you look at that, you've got 3. Where's the other odd one? V looks like it's got 3, because if you look 4, 2, 4, 4, and 2, so you've got to finish at V, the other odd one. Okay, so Zoe begins skating at ramp X, so we're starting here, and she's following a Hamiltonian path. Now Hamilton is about every vertex, so we need to go to every vertex in this situation, and the path she chooses does not include the 2 rough tracks, so we can't have that and we can't have that. So what's our path going to be? Well, obviously we have to do this because there's no other way around it, and there probably is more than one answer here, but that looks pretty good. So now you need to write down the path. So we went X, Y, T, U, Z, V, W, and done. Now in the previous question, you might have got a different answer. That's okay. There actually were 2 answers. I only showed you one. But this one is asking in how many ways can we do a Hamiltonian cycle starting at X and including the rough tracks. A couple of tricks to note here. So we're starting at X and we go to Y, T, U, Z, V, W, and then X again. So the first thing to note is that we've gone X, Y, T, U, Z, V, W, and that was going that way. But we've also got to remember we included X. Start with X, ends with X. That's okay on a cycle. You do repeat the letter. Doesn't mean you're actually repeating the vertex because you haven't gone past it again. But if we went the same trip this way, so instead of going that way, we're going the other way, we can just actually take those letters and reverse them. X, W, V, Z, U, T, Y, X, and we've got 2 ways so far. So even though it looks like one cycle, because you can go both ways, that's actually already 2 ways. Now we just got to find the other way. So in both cases we have to start at X. So if we start at X, we can come down here to T to U, but how about this time we go V, Z, W, X. So if we write that one up, that is X, Y, T, U, V, Z, W, X. And of course, since we were going this way, we can take it back the other way. Probably try and do that in green this time. And so that's going to be X, W, Z, V, U, T, Y, X. And I think you'll find that there really isn't any other way of doing that. But you notice we did use the rough track. So How many ways to do this? 4.